Hello everyone, my name is Parth and today I'm going to talk about flexible semiconductors. This is the outline of the topics which I'm going to discuss under semiconductors. Starting with introduction, amorphous silicon has long been the king of flat panel displays. It began its reign in PC monitors and then TVs and then concrete netbooks and also to smartphones, but no other substance was as suitable for thin film transistors than sit behind a display's hundreds of thousands of pixels and turning each one on and off. But soon the domination of the amorphous silicon will pass because it cannot provide what coming generations of electronic products will require. The next generation LCD TVs will be refreshed at a rate of at least 240 times a second, which is 2 to 4 times as quickly as today's versions. That's why they'll provide sharper action sports and movies. Three-dimensional displays will need refresh rates twice against as high to provide all that fast motion goodness to each eye. So, talking about thin film transistors, at present the thin film transistors or TFTs are made up on glass, and the semiconductor which is used is amorphous silicon for today's displays that we can see in laptops or phones or anything else. But in future we want to make the thin film transistors on plastic, and using that we can have a variety of applications as high definition televisions, flexible displays, anywhere we can fit. And so what would be the material which you want to use to make that thin film transistors on plastic? So thin film transistors on plastic can be made using these materials such as amorphous oxide. Then the other is IgZO, or we can call it as indium gallium zinc oxide. And also there is another material known as IZO, that is indium doped zinc oxide. Okay, so first we are going to talk about amorphous oxides. Using amorphous oxides, we can make thin films that are transparent and electrically conductive both, which is why they already serve as a see-through electrode layer in displays and solar cells. We believe that amorphous oxides could do more than simply serve as a passive electrode. They could also replace amorphous silicon as an active semiconducting material that does the heavy lifting as the channel in thin film transistors. So in amorphous oxides, charge can zip through 20 to 40 times as fast as in amorphous silicon. So the higher it gets, the faster a transistor can switch. So using this amorphous oxides, it can be laid down or even printed on plastic sheets to make paper-like displays, and that would be really a good material option in place of amorphous silicon. So now we will try to understand amorphous oxide structure. As we can see on the left side, the crystalline solid atoms line up in an orderly 3D array, while in polycrystalline solid, which is in the middle, is made up of smaller crystalline chunks. And on the right side, in an amorphous solid, perfect order goes out the door. That means an irregular arrangement lends itself to a formation of smooth, uniform films, but also slows down the charged particles, which is a mixed blessing for TFTs. So this random arrangement of atoms, which tend to give amorphous material smooth surface and uniform structure when they are produced as films, which you can measure anywhere from 10 to hundreds of nanometer thick. And these films are more robust than polycrystalline ones, whose grain boundaries acts like shunt paths for impurities. Water vapor, for instance, would more readily penetrate polycrystalline films. That's why amorphous silicon has wrested the domain of thin film transistors from crystalline solid. These are the advantages of amorphous oxides. Firstly, it has a wide controllability of carrier concentration. Also, it has a high optical transparency in invisible regions, and it also has a capacity to work at room temperature and has got a very large area for deposition. Last but not the least, it has unique carrier transport properties too. After amorphous oxide, now we are going to talk about indium gallium zinc oxide, or also known as IGZO. So IGZO thin film transistors are used to make flat panel displays. IG0 TFTs are used because it has 20 to 50 times the electron mobility of amorphous silicons, which will help achieve our goal to make bigger, high resolution and better displays. So thus it is considered to be one of the most promising TFTs to be used to make OLED displays. So now we will talk about advantages of indium gallium zinc oxide, or IGZO. So first and foremost advantage of IGZO is that it produces more pixels per area and thinner wiring than current amorphous silicon transistors, which will result in higher resolution apparently. And currently amorphous silicon LCD displays make up the largest percentage of smartphone display market, but IGZO is also making its move to get into the mobile displays because it is smaller and more compact, and also it results in a clearer picture as compared to amorphous silicon display. One of the other benefits of indium gallium zinc oxide TFT is that it is highly scalable, allowing for much higher resolution displays with greatly increased pixel densities. Now, higher electron mobility also lends itself to improved performance when it comes to refresh rate and switching pixels on and off. Sharp has developed a method of pausing pixels, which is really great, which allows them to maintain their charge for a longer period of time, which again will improve battery life as well as help create constant high quality image. The third advantage of indium gallium zinc oxide TFTs is that it helps achieve less noise influence. Using IGZO transistors, it creates almost no noise, which is an improvement in the sensitivity of touchscreen technology. Now, in conventional touchscreen panels, which were made up of amorphous silicon TFTs, the electrical noise created by a continuous signal interferes with the sensitivity of touchscreen. But using IGZO TFTs, when paused, the IGZO creates almost no noise, allowing the sensors to operate at high sensitivity. Until now, we have discussed that we can use amorphous oxide or indium gallium zinc oxide TFTs in place of conventional amorphous oxide TFTs, which had the advantages of IGZO and amorphous oxide is that they are scalable and makes less noise and gives high resolution. But we also want to consider the fact of cost, so we will try to discuss about indium dope zinc oxide for that purpose. And the indium dope zinc oxide, or IZO, also has the same advantages of being highly transparent, then working at a room temperature, and also has a very high field effect mobility. It is also fast, but the main advantage of indium dope zinc oxide is that it is low in cost. Now we will discuss some of the issues. There are a few issues which needs to be solved, such as stability of the devices and making them inexpensive, such as like working on materials such as IZO, that is indium dope zinc oxide, or zinc tin oxide, which incorporates less expensive materials and can be more easily fabricated as thin films. And also we want to discover a p-type amorphous oxide semiconductor. Now coming to conclusions, there's a little doubt that amorphous oxide semiconductors can replace amorphous silicon. The only question is when. The answer mainly depends on how long it will take to develop large-scale manufacturing capability, but the oxide thin film transistor fabrication process is very similar to that used for amorphous silicon devices, so the display industry can leverage much of its existing infrastructure and know-how. Also, we want to keep an eye on the innovations in display back panels, which aren't going to stop with IGZO, as companies are already investing in the next wave, aiming to further improve energy efficiency and display performance. Two examples worth keeping an eye on are amorphous metal nonlinear resistor, that is AMNR, and CBRITE. So there will be future innovations too, and which will help us get better, brighter, and good displays. These are some of the references which I have used to make this presentation. Thank you.